to thank Claudio for setting the stage this morning, because what he's described is the case for precursor missions. And what I'm going to talk about here in a presentation that Paul Gilster and I actually put together for the International Space Development Conference, which was held in Huntsville last year, is talking not only about the far term, but it's kind of an overview to interstellar travel and the advanced propulsion technologies that have been examined over the years, that our follow-on speakers will be going into a lot more detail to describe. So I'll try not to go into a lot of detail on the description of the technologies and leave that for the follow-on folks, but I wanted to kind of give an overview of where we are in terms of capability and thoughts for interstellar travel. First question I get asked is, well, you know, who are you to talk about interstellar travel? When I go to the Journal of the British Interplanetary Society, your name's not there. I see all the Greg Matlofts and Claudio Marconis and all these other folks, but just by way of background, I got involved in this field a long time before working for NASA. I've been a science fiction fan ever since I can remember. But I had the privilege of having the coolest job title in the universe about 10, 15 years ago when I was manager for NASA's Interstellar Propulsion Technology Project. And that was working with the folks at JPL that Claudio just mentioned, not only on propulsion options for the 1000 AU mission, but also for something called the Interstellar Probe, which I'll talk about here in a few minutes. But of course, I also watch Star Trek. And I believe that this is a future that is open to us someday if nature gives us a few loopholes, and even if nature doesn't give us the loopholes within large time spans. And I'm thinking in terms of not just human lifespans, but within terms of the species. There is no reason that we can't have the galaxy. And as we go through the day, we're going to get toward the end of the day and hear a panel discussion on the Fermi paradox, where Stephanie and her folks will be talking about the fact that an intelligent tool-using species should already have the galaxy, and how we might someday do that ourselves, which unfortunately we won't live to see. Of course, I'm inspired by many of the same things that inspired many of you. Again, I'm a science fiction fan from way back. Watching these science fiction movies got me interested in space and space travel, and you may recognize some of these as shows that you may have been interested in and have read yourself, and hopefully we'll set the stage for something realistic as opposed to what we find in the movies. I'd like to mention that we have in the audience today not just scientists and engineers. I happen to know personally that we have folks from the business community, we have artists, we have a physician, at least one, and the common theme for all of us is the love of space travel and the thought of going to the stars. And so I'd set the stage for how tough this problem really is. Even those of us working in the field sometimes forget how really hard it's going to be to go to another star. And that's the purpose behind this chart. This chart's a log scale that begins in our solar system, starting at the unit 1 astronomical unit, 93 million miles. Sorry, Claudio, we're using English units in the US here. And when you get out to Saturn, you're approximately 10 AU. Jupiter's at about 5. You've got Pluto, which is out there at about 38 astronomical units, so 38 times 93 million miles. The gravitational lens mission at about 550 astronomical units. When you get to that point, you're out beyond here, the edge of what the solar physicists consider the boundary of the solar system, which is the heliopause, until you get to the nearest star system, which is the Alpha Centauri system, which isn't a measly 550 astronomical units away. It's about 250,000 astronomical units away. Just to put this into a concrete perspective, if we shrink 1 astronomical unit to be 1 foot on the scale that we're talking about here, Jupiter is about 5 feet away, Pluto is about 38 feet away, and the nearest star is about 47 miles away. We are incredibly isolated. This is a huge challenge. Going to another star will undoubtedly be the largest engineering challenge when we finally undertake this that the human race will ever endeavor to take. So even those of us, and those of you who live this, and who have thought about this in your career, Al, you've thought about this, for me, I am awed at the distances. And I wanted just to remind everyone of what we're talking about here when we talk about interstellar travel. The Voyager spacecraft are the most distant spacecraft we've sent out. They are cruising along at a very small fraction of the speed of light, 0.006% C, roughly, about 3.5, almost 4 astronomical units per year. Wow, that's a clip. That's moving out pretty good. At that speed, it'll take about 74,000 years to get to the nearest star system if they were going in the right direction. So they're not. So we have a long time to go, and what's really neat to me as someone who is in the upfront work of designing spaceships for the Advanced Concepts Office at NASA, these spacecraft are still working, okay? Thanks to their plutonium power pack, keeping them warm and giving a little bit of power to send back data from the edge of our solar system. They are still functional. Excellent. Where are we going? Well, I'd like to talk just briefly in this overview about near, medium, and far-term options for interstellar travel. First off, the interstellar probe, how I got into this mess. I was asked to be the propulsion lead for a study led out of the Jet Propulsion Laboratory. It was an international study to do a mission to the heliopause. Now, the heliopause is of interest to the solar scientists. If you work within NASA, you find out that technologists don't get to design missions. They have to have a reason to design a mission. And in this case, the scientists, the solar physicists, want to go to this boundary where basically the outward radiation pressure from the sun, from our star, is exactly balanced by the inward radiation pressure from all the stars in the galaxy coming in. And that region is the heliopause. And there's a little bit of uncertainty as to exactly where that is. There's a region that's maybe potentially 50 to 100 AU wide that forms this amorphous boundary at the end of the solar system. There's some discussion as to whether one of the Voyager spacecraft has already entered the heliopause region. The goal of this mission, though, was to launch a mission dedicated to studying the heliopause and to get data back within the professional lifetime of the people who launched the spacecraft. The challenge for that means that the goal that was given to me, the propulsion guy, was get the spacecraft there within 20 years of launch. Why 20 years? Because by the time a scientist has the professional pedigree to be the principal investigator for a mission to the heliopause, he or she's going to at least be mid-career, which means in their 40s. And if you don't get the data back within 20 years, they're going to be retired or dead by the time the data starts coming back. And at best, the graduate students or the PI's grandchildren will be looking at the data, right? So the scientists had a very selfish motivation. Let's get the data back. There's also a pragmatic motivation. Voyager's been lucky. It's lasted for as long as it has, but we can't guarantee that a spacecraft's going to last a long time. We can design one to last for 20 years. 100 years is going to be a challenge. So there are a lot of practical reasons for designing a spacecraft to do this. And we looked at different options. And I'm going to tell you today my opinion, technical, professional opinion, that this mission can be done. And there are various ways we can do it. One of those ways is using something called electric propulsion. Rather than giving a full lecture on electric propulsion, I'm just going to say that it's a method of propulsion that doesn't use chemical combustion to give you thrust. You use electromagnetic fields to accelerate your propellant out the back of your spacecraft to give you a very low thrust but very efficient propulsion. Electric propulsion is about 10 times more efficient per pound of fuel to get moving for a spacecraft to go through space. So you get about 10 times more kick per pound of fuel with electric propulsion systems than you do with chemical combustion. It's a continuous low thrust system. We've built these. There's one, the United States has built them, Europe's built them, Japanese are building them. This is not a new technology in the sense of untried. What is new is the fact that this would have to operate at fairly high powers and probably require a nuclear power source to drive it. In Oak Ridge, it's appropriate and okay to talk about the N word. And about a 100 kilowatt reactor is what we determine, 100 kilowatt electric output to drive some multiple 10 kilowatt electric propulsion thrusters, which we've built, by the way. The next engine could be used for this, could power a ship to go do this mission. There is no funding to do that. We looked at it. There was a mission that was almost a precursor called the GEMO mission, but that was canceled due to lots of reasons. Chief among them was a funding issue. But electric propulsion will work. We can get a trajectory and a spacecraft today to get us to 250 AU within 20 years of launch with sufficient funding and effort. And this is to show you that electric propulsion systems are real. This is a picture of the testing at the Glenn Research Center that we did on one of the engines in a project I managed. And down here on the right is a small Hall thruster with a Pepsi can for scale to show you what some of these electric propulsion systems look like at smaller scale on existing spacecraft. So these are very real. You're also going to hear today a more detailed talk on solar sailing from Greg Matloff. Shameless plug, our book on solar sailing is available at the back table. I'd like to point out that there has been significant progress in the last 10 years for solar sail. Back in the mid-2000s, I managed the In-Space Propulsion Technology Project, where we actually did ground demonstrations of 2 different solar sail configurations. These are actual ground tests in the world's largest vacuum chamber. It was 2 solar sail ideas. This is 100 feet across. This little dot here is one of the engineers inspecting a quadrant of the sail. These sails were deployed from a box not much bigger than this box that the projector is sitting on here, with very thin solar sails, carbon composite booms that deployed out 50 feet on each side, and fully functional sails with 2 different technology approaches. Since that project was canceled, the Japanese came in and said, well, hey, the Americans are out of the race, let's go fly one of these puppies. They did. This is a picture from space of Icarus, which is the Japanese solar sail launched last year. It was launched on a spacecraft on its way to Venus. This is an in-flight picture from Icarus on its way to Venus. It's slightly smaller than this. Instead of 20 meters on a side, it's 14 meters on a side. This spacecraft is deployed in full sunlight that measures propulsion. They are on their way. And in communication with the PI for this project, we're building the next sail for a science mission that's going to go to the outer planets. This photograph was taken with a little coffee can-sized spacecraft that kicked off with a small camera. Imagine your iPhone camera, a little bit better than that. It took a picture of the sail, beamed the picture back to the spacecraft, which had a higher power transmitter with something back here. So the Japanese, they're on their way. This is an artist concept of the NanoSail D, which was out at NASA Marshall, and the Ames Research Center. It was a CubeSat. This is a much smaller sail. It didn't ever really solar sail much, about 10 square meters in area, and it deployed and flew in Earth orbit on a CubeSat. And CubeSats are small spacecraft, very, very small, about much smaller than this tabletop. So solar sails are no longer theoretical. They're flying, okay, which is astounding. There is a roadmap for the development of solar sails to go to some of the more ambitious approaches for interstellar travel. I always like to mention a friend of mine and a professional colleague who inspired me as a youth and inspired me as a professional when he worked with us at NASA, and that's Dr. Robert Forward. Some of you may know or have read some of his stuff. Bob Forward was one of the pioneers in laser sailing and microwave sailing, and the idea here is that we begin today with some of these small solar sails and eventually lead up to the very large sails that would enable true interstellar travel. Now, I mentioned the solar sail because on the Interstellar Probe team, that was the solution that the team recommended to both NASA and ESA as the propulsion system for the Interstellar Probe to go out to 250 astronomical units. And it would be a solar sail of about 200 meters on a side. We're flying 14 meters now. We've designed sails that could be up to 80 meters on a side. NASA recently selected for flight validation a company, Lagarde, who built one of the sails for us in the In-Space project, where they will actually demonstrate a sail of not quite 80 meters, but it's going to be a fairly large solar sail, and it will be the first American deep space flight of a sail in about 3 years. The next step beyond that would be scaling it from about that size up to about 200 meters. And based on what we know about the engineering, that is possible. It's just a matter of going and doing it to enable this mission. I'd like to leave the Interstellar Probe at this point in terms of realistic options and talk about one that was discussed years ago and is still being discussed, and there's an excellent book on Project Orion. And that is the idea of using a new use for thermonuclear devices. I think here in Oak Ridge they euphemistically call them the physics package, which always kind of bothered me, but well, that's a topic for another discussion. And the idea is that you use very small nuclear explosions under a very large spacecraft with some shielding in terms of a big plate and a shock absorber, and use the impulse from the explosion to accelerate your spacecraft. If you read Larry Niven and Jerry Pournelle's Footfall, you'll find out that this is something that was talked about in a very realistic way of how you could actually get from the Earth to space using something like this, although I think the side effects of the bombs going off would be a bit of a problem. The idea here is that you have a very controlled series of small nuclear detonations to accelerate a spacecraft, something on the order of the size of an aircraft carrier. This is not for the faint of heart. This is for massive deep space interplanetary travel. very feasible for taking humans to the outer solar system if we ever decide to do that, and certainly an option for deep space early interstellar missions. There are lots of issues associated with design. Can you get the efficiency of the reactions to occur? You know, what does really the spacecraft look like? To my knowledge, there has not been an incredibly detailed study done on an Orion-propelled spacecraft, but there have been enough proof of concepts to show that this is the kind of thing that can work. It would have to be something pretty dramatic to get us to be able to do something like this from the ground to space. As someone who works for NASA and is limited in what we can launch into space, I think doing an in-space assembly of something like this with existing launch capability would be a real challenge. Although NASA's new SLS launch vehicle is supposed to enable about 100 metric tons to low Earth orbit per launch. So, you know, this is in the realm of possibility in the future if we wanted to do something like this. It was envisioned, by the way, when this was being studied in the late 50s and early 60s, you can see down here on the bottom, that they envisioned a crewed mission to Saturn by 1968. Talk about ambitious. Really, really cool stuff. More on the Orion starship. It could conceivably get to about 3% of light speed with trip times of hundreds of years. Amazing, hundreds of years instead of thousands. We're going to hear a lot more discussion on fusion. We are very lucky today. We have folks from Project Icarus, who are not Ikaros, which is the Japanese solar sail, but Icarus, which is the fusion drive starship team, which is developing a concept for a fusion power drive to another star. So I will defer most of that. But I will say that in terms of the physics of this, we looked at, as I mentioned, for the Interstellar Probe, a fission-driven power system for an electric propulsion spacecraft. This would use the much more energetic fusion reaction to get a lot more energy to power our starship to the stars. Fission is just not practical for interstellar travel. As efficient as fission energy is, and as much power as we get out of the fission reaction, splitting atoms, when we're talking about going the distance to the stars, it really doesn't have the energy density you need to get a realistic trip time for a spacecraft to have a fission-driven system to go to the stars. You've got to go to something more energetic, which is a fusion drive. I'm not going to steal the thunder of the Icarus team, so I'm going to talk about the precursor studies, which were done on Project Daedalus, British Interplanetary Society study, looking at a fission-driven spacecraft. You can see this too is fairly massive. They took the designs of 60s and 70s of what we knew about engineering and advanced propulsion and fusion systems and came up with a pretty good design for a fusion-driven spacecraft. And you can see here that it required in their studies about 30,000 tons of helium-3. Helium-3 is a pretty rare isotope of helium. It's thought to be embedded in the lunar soil. There's some in the Earth's atmosphere. It's my understanding there's a lot in the Jovian atmosphere. So you can almost envision a solar system-wide effort to collect and store the helium-3 that would be needed for one of these interstellar voyages. You can't think small when you talk about true interstellar travel. Going back to the solar sail approach, if you convert that to a laser-driven sail, which I think Greg's going to talk about, we're talking about sails the size of Texas. We're talking about focusing lens at Jupiter to keep the laser light focused on the sail to keep accelerating it with hundreds, if not 1,000-kilometer wide inflatable Fresnel lenses. And we're talking about lasers in solar orbit that are on the order of terawatts of power, which is on the order of the total global energy output of humanity today. So when we talk about fusion-driven starships and laser-driven solar sails, it's not for the faint of heart. It is a challenge, and it's going to be a challenge for our entire civilization to undertake these voyages, unless we have some pretty dramatic breakthroughs in physics. The last advanced concept, which we did not consider for the Interstellar Probe, is antimatter propulsion, and Harold Garish from NASA Marshall, if he's recovered from the flooding of his, near flooding of his lake house, we'll be talking about at 11:30, and this is the capturing antimatter and using the annihilation of matter and antimatter, which is the most energy efficient reaction we know of today to power a starship. Just think of matter and antimatter as being a big battery, or if it releases prematurely, a big bomb. So you'd have to store antimatter in a really good vacuum in some kind of a magnetic field. You'd have to store positively charged electrons, which is not the way to go. You'd probably want to go with antiprotons. These are created, as a matter of fact, in the world's particle accelerators at CERN and other places. They're not, these accelerators do not have the capability to generate massive quantities of antimatter. In fact, the global production of antimatter is on the order of nanograms per year. And for an interstellar voyage, what you really need is on the order of kilograms. So you've got to move all those zeros from the wrong side of the decimal place to the other side of the decimal place in order to get the amounts of antimatter you need to undertake a voyage to the stars. But kilograms of antimatter compared to tens of thousands of tons of helium-3 and other fuels can certainly make a difference for how we do true interstellar travel. And Harold, I hope, will relate the story of how they had planned to collect and bring to Huntsville antimatter from Fermilab about 10 years ago to be the first real test of an antimatter propulsion system, but that did not occur. I want to mention the hopes for the future. You know, technology is really just applied science, and there are lots of interesting things happening in physics today. Dark energy, dark matter, things we don't really understand in the universe, claims not with cold fusion-like fervor, but with real scientific rigor of potential faster-than-light travel by neutrinos. We're in an exciting time in physics. We may be uncovering that our theories may not be complete. And if that's the case, maybe some of the things that we thought previously impossible that are in the realm of science fiction might become possible. There have been efforts to try to investigate these things. The problem with that, as Mark Millis would tell you from his experience managing the Breakthrough Propulsion Physics project for NASA at NASA Glenn, is you get some really good science, some real cutting-edge research, and you get lots of quacks. And I'll tell you, from my job at NASA, about once a month, I get an email of somebody wanting me to review their propulsion system, which just so happens to be, you know, infinite ISP, infinite efficiency, violates the second law of thermodynamics. And so you got to be careful that you get all kinds of people coming out of the lunatic fringe. And courtesy of Microsoft, we also have products that creep up. The project for Breakthrough Physics ran for a while and was canceled. It tends to not get a lot of support within NASA. The science community tends to kind of frown on this a little bit. And I think that's a fine line you walk between being creative and innovative and being kind of over the edge. And Mark walked that very well and had managed a very excellent project, and it was unfortunate that that too was canceled. The results from that and some of this leading edge speculative physics can be found in an AIAA monograph called The Frontiers of Propulsion Science. Some really interesting, very credible peer-reviewed essays and technical papers written by some of the folks in that field. So I guess in conclusion, I'd like to say that we've got the Voyager. We are ready to take that first step. It's just a matter of somebody saying, go, to take that first step for the interstellar probe. It would not be too much of a stretch beyond that, Claudio, in my opinion, to undertake this first mission to the gravity lens. It's a matter of political will. It's not a technical problem. We can solve that problem. We know how to get there for these early precursors. And in conclusion, I have to do a shameless plug for three folks in the room. Coming in May, and I'll pass this around, there's a science fiction anthology coming out from Baen Books that I had the privilege of being co-editor with Jack McDevitt. It's called Going Interstellar. Richard Obasi, Project Icarus, Greg Matloff, and I have written some companion science essays, popular science essays, that will be interspersed with science fiction stories from Ben Bova, Michael Bishop, Mike Resnick, and others about interstellar travel. And I was real excited to learn today, well, not today, this week, it was right before we were in Iowa, that Baen has decided to commission a teacher's guide to go along with this, and they're going to send this collection of stories to high schools with science teacher guide for the high school students to be able to use that. So, yeah, I'm pretty excited. I had no idea that they were going to do that. So please, when this comes out, it might be of interest to you. And if you know of some schools, you might encourage the schools to pursue getting this into their schools for the kids to read. There will be a teacher's guide, and I hope to see that sometime in the near future. So with that, I'll close and take questions if there are any.
Question for both you, and I'll address it to Richard also. When the Daedalus team did their original study on mining helium-3 from outer-planet atmospheres. We didn't know very much about outer-planet atmospheres. Right now we know a bit more. How do we suspend by balloon helium-3 mines in an atmosphere which is affected by lots of lightning? It would occur to me you would have to have a very long ground wire.
You know, Greg, I have no idea.
To
the best of my knowledge, there hasn't been a good design study
Yeah.
doing that, to the best of my knowledge. Richard, do you have any comment?
Yeah, we're looking at the possibility of using scramjets in the atmosphere because the higher density means that, and it's better utility of the scramjets, but you know, that's something that's ongoing in the team.
Okay.
Yes.
You mentioned that you thought that fission did not qualify because of the energy density. Back in the late 50s and early 60s, everyone took it for granted that we were going to have nuclear fission-propelled rockets. And in fact, the Minerva was built and tested, and John Powell of Brookhaven greatly improved the design of the particle bed reactor and so on. A very important paper came out of JPL right around 1960. They published an annual volume of advanced papers, and unfortunately I can't remember the author's name, but he pointed out the very great importance of staging of nuclear rockets. The reason we got to the moon was that the Saturn V was a 3-stage rocket. The reason that Curiosity is on the way to Mars now is 2 optimized stages. Well, what he found was that 10 stages of fission fixed the problem that you're worried about, and in fact could achieve about 2/10 of the speed of light quite readily. So I think that paper needs to be dug up and reviewed.
Well, I missed that one. When we did our assessments, we looked at nuclear thermal rockets, and we looked all the way from the solid core up to the gas core. And we found that for precursor missions going to the heliopause or the 550 AU, that you could, in fact, potentially do a nuclear thermal rocket. But we still didn't realize that you could do it for Alpha Centauri.
Well, you get the point about the
I get the point on staging, and I'll be glad to look at that and revise, absolutely.
In fact, you could also do your plasma electric propulsion stage the same way, because I think when you put that in, it's going to change things.
We'll certainly take a look at that. Thank you, sir. Probably have time, I'll police myself, probably time for one more question, and then we can get down.
How does the thrust from the solar cell system compare, say, to the ion propulsion, electric propulsion?
It depends on deployment distance from the sun. Both of them can achieve an in velocity that's comparable. A solar sail, you would probably, with a pure solar sail for the Interstellar Probe mission, you would go on a very close solar flyby to take advantage of the inverse square law to maximize the thrust on the sail and actually stop thrusting at about Jupiter. And you get all your acceleration in the inner solar system. So I would say that the thrust, not the total delta V, would be higher from the sail than it would be on the nuclear electric system, because the nuclear electric system, you would keep thrusting beyond the orbit of Jupiter to get the delta V required to go to the heliopause. So the thrust, contrary to what you might think, might actually be higher on the solar sail for the inner solar system, for the Interstellar Probe. On the deep, ultra deep space, I'm not sure how that would compare. It depends on the power system and those kinds of things. Was there a question over here that I missed? And then, no?
NASA just created a new office. It's been pretty much getting all of the news recently. And I was really wondering, because it sounded like it had a lot to do with future types of propulsion.
It does.
And what is the relationship between what your office is doing, and are they looking at any of these types of?
Yeah, the Office of the Chief Technologist and the NASA's technology project is actually funding this first flight demonstration of the solar sail, as well as some other technologies. And I have something unrelated to interstellar travel, a tether propulsion. There's going to be some funding from that office right now. So, yeah, that's also here. All right, thank you very much.
One other question. Curious about, I enjoyed very much Claudio's concept. The other way to go is just a large antenna, large dish. What's the answer to how large must this dish be to rival the sun in gain?
I'll let Claudio answer that while I'm taking my computer off and getting my next speaker up.
I don't know. Sorry to disappoint you so much. I don't know, you see, these topics have not been explored really so far. Perhaps there were technical
papers in some journals. But first of all, they come from different minds and different groups of researchers. And second, you know, there are ideas that pop up cyclically from time to time. So someone had already some ideas. I remember Jörg Ströbel, you probably remember that, who once wrote a paper in JDAS titled Hollow Body Solar Sail. Well, this is basically what I suggest, that is an inflatable thing, which is concave on the side of becoming an antenna and the other way around on the other side. Okay? But this was just a paper. We need some real design here. And that can be designed only if a company decides to set up a group or a research institution and you know, devote some time to that, and then finally a serious design will come out. I'm sorry, but I cannot say more than that.
Thank you.